Students, so in the previous video we have just talked about the conservation of work. So let's just start with various forms of energy and the law of conservation of energy. In the previous section we have discussed mechanical energy. We have seen that it can be classified into two distinct categories, one based on motion, namely kinetic energy, the other on the configuration, namely potential energy. Energy comes in many forms which transform into one another in ways which may not often be clear to us. Heat. We have seen that the frictional force is not a conservative force. However, work is associated with the force of friction. Example number 6.5. A block of mass m sliding on a rough horizontal surface with speed v0 comes to a halt over a distance x0. The work done by the 0 square divided by 2 is equals to fx0. If we confine our scope to mechanics, we will say that the kinetic energy of the block is lost due to the frictional force. On examination of the block and the table, we will detect a slight increase in the temperatures. The work done by the friction is not lost but is transferred as heat energy. This raises the internal energy of the block and the table. In winter, in order to feel warm, we generate heat by vigorously rubbing our palms together. We shall see later that the internal energy is associated with easeless, often random motion of molecules. A quantitative idea of the transfer of heat energy is obtained by noting that 1 kg of water releases about 42,000 joule of energy when it cools by 10 degrees Celsius. Chemical energy. One of the greatest technical achievements of humankind occurred when we discovered how to ignite and control fire. We learned to rub two flint stones together, got them to heat up and to ignite a heap of dry leaves, which then provided sustained warmth. A matchstick ignites into a bright flame when struck against a specially prepared chemical surface. The lighted matchstick, when applied to a firecracker, results in a spectacular display of sound and light. Chemical energy arises from the fact that the molecules participating in the chemical reaction have different binding energies. A stable chemical compound has less energy than the separated. Then the products of the reaction, heat is released and the reaction is said to be an exothermic reaction. The reverse is true, heat is absorbed and the reaction is endothermic. Coal consists of carbon and a kilogram of it. When it burns, releases about 3 into 10 raised to 7 joule of energy. Chemical energy is associated with the forces that give rise to the stability of substance. This force bind atoms into molecules, molecules into polymeric chains, etc. The chemical energy arising from the combustion of coal, cooking gas, wood, and petroleum is indispensable to our daily existence. Electric energy. The flow of electrical current causes bulbs to glow, fans to rotate, and bells to ring. There are laws governing the attraction and repulsion of charges and currents, which we shall learn later. Energy is associated with an electric current. An urban Indian household consumes about 200 joule of energy per second on an average. The equivalence of mass and energy. Till the end of the 19th century, physicists believed that in every physical and chemical process, the mass of an isolated system is conserved. Matter might change its phase. Example, glacial ice could melt into gushing stream, but matter is neither created nor destroyed. Albert Einstein, however, showed that mass and energy are equivalent and are related by the relation E is equals to mc square, where c is the speed of light in vacuum is approximately 3 into 10 raised to 8 meter per second. Thus, a staggering amount of energy is associated 10 raised to 16 Joule. This is equivalent to the annual electrical output of a large 3000 megawatt power generating station. Nuclear energy. The most destructive weapons made by man, the fission and fusion bombs are a manifestation of the above equivalence of mass energy. On the other hand, the explanation of the life nourishing energy output of the sun is always based on the above equation. In this case, effectively, four light hydrogen nuclei fuse to form a helium nucleus whose mass is less than the sum of the mass of the reactants. This mass difference, called the mass defect, delta m, is the source of energy delta m c square. In fission, a heavy nucleus like uranium 90 to uranium 235 is split by a neutron into lighter nuclei. Once again, the final mass is less than the initial mass, and the mass difference translates into energy, which can be tapped to provide electrical energy as in nuclear power plants, or can be employed in making nuclear weapons. Strictly, the energy delta E released in chemical reaction can also be related to the mass defect delta M is equal to delta E divided by C square. However, for a chemical reaction, this mass defect is much smaller than for a nuclear reaction. Table 6.3 lists the total energy for a variety of events and phenomena. So here are some of the phenomenon. Big Bang, that is 10 raised to 68 joule. Radio energy emitted by the galaxy during its lifetime, that is 10 raised to 55. Oceans, hydrogen in fusion, 10 raised to 34. Rotational energy of the earth, 10 raised to 29. Annual solar energy incident on the earth, 5 into 10 raised to 24. Annual wind energy dissipated near Earth's surface, 10 raised to 22. Annual global energy used by human, 3 into 10 raised to 22. Annual energy dissipated by the tides, that is 10 raised to 20. Thunderstorm, 10 raised to 15. So there are so many new energy to break one bond in DNA, 10 raised to minus 20. Discharge of a single neuron, 10 raised to minus 10. Typical energy of a proton in a nucleus, 10 raised to minus 13. So every subject or every particular value having some value of their energy in a joule. Examine table 6.1, 6.3 and express the energy required to break one bond in DNA in electron volt, the kinetic energy and the daily intake of human adult. तो उसको आप आराम से कर सकते हो कन्वर्ट. डिवाइड करना है 1.6 इंटू 10 raised to minus 19 से. ठीक है. We point out a common misconception created by newspapers and magazines. They mention food values in calories and argue us to restrict diet intake to below 2400 calories. What they should be saying in 1 kilocalories and not calories. A person consuming 2400 calories a day will soon starve to death. A food calorie is 1 kilocalorie. The principle of conservation of energy. We have seen that the total mechanical energy of the system is conserved if the forces during work on it are conservative, such as heat, light, and sound. However, the total energy of an isolated system does not change as long as one accounts for all forms of energy. Energy may be transformed from one form to another, but the total energy of an isolated system remains constant. Energy can neither be created nor destroyed, since the universe as a whole may be viewed as an isolated system. The total energy of the universe is constant. If one part of the universe loses energy, another part must gain an equal amount of energy. The principle of conservation of energy cannot be proved. However, no violation of this principle has been observed. The concept of conservation and transformation of energy into various forms brings together various branches of physics, chemistry, and life science. It provides a unifying, enduring element in our scientific pursuits. From engineering point of view, all electronic communication and mechanical devices rely on some forms of energy transformation. Our next topic is power. Often it is interesting to know not only the work done on an object but also the rate at which this work is done. We say a person is physically fit if he not only climbs 4 floors of a building but climbs them fast. Power is defined as the time rate at which work is done or energy is transferred. The average power of a force is defined as the ratio of the work W to the total time taken T, that is PAV is equals to WT. The instantaneous power is defined as the limiting value of the average power as time interval approaches 0. P is equals to the instantaneous power can also be expressed as P is equals to FdR divided by dt, that is Fv, where V is the instantaneous velocity when the force is F. Power, like work and energy, is a scalar quantity. Its dimensions are m, L, 2, t minus 3. In the SI, its unit is called watt. The watt is 1 joule per second. The unit of power is named after James Watt, one of inventors of the steam engine in the 18th century. There is another unit of power, namely the horsepower. That is 1 horsepower is 746 watt. This unit is still used to describe the output of automobiles, motorbikes, etc. We encounter the unit watt when we buy electrical goods such as bulbs, heaters, and refrigerators. A 100-watt bulb which is on for 10 hours uses 1 kilowatt hour of energy. It is 100 into 10, that is 1000 watt hour. 1 kilowatt hour, that is 10 raised to 3 into 3600 second, that is 3.6 into 10 raised to 6 joule. Our electricity bills carry the energy consumption in units of kilowatt hour. Note that kilowatt hour is a unit of energy, not a power. An elevator can carry a maximum load of 1800 kg, is moving up with a constant speed of 2 meters per second. The frictional force opposing the motion is 4000 Newton. Determine the minimum power delivered by the motor to elevator in watts as well as in horsepower. The downward force on the elevator is F is equals to mg plus ff. Hence 22,000 into 2, that is 44,000 watt, that is 59 horsepower. Next topic is collisions. In physics, we study motion. At the same time, we try to discover physical quantities which do not change in physical process. The laws of momentum and energy conservation are typical examples. In this section, we shall apply these laws to commonly encountered phenomena, namely collisions. Several games such as billiards, marbles, or carom involve collisions. We shall study the collision of two masses in an idealized form. Consider two masses m1 and m2. The particle m1 is moving with a speed v1I and the subscript I implying initial. We can consider m2 be at rest. No loss of generality is involved in making such a selection. In this situation, the mass m1 collides with the stationary mass m2 and this is depicted in figure 6.12. मतलब यहाँ से देखो m1 उसको स्ट्राइक करा है m2 के ऊपर, तो m2 इस डायरेक्शन में चला गया, m1 दूसरी डायरेक्शन में चला गया. द मास m1 एंड m2 फ्लाई ऑफ इन डिफरेंट डायरेक्शंस. वी शैल सी दैट देयर आर रिलेशनशिप्स which connect the masses, the velocity and the angles. Okay, so next topic is elastic and inelastic collision, जिसके बारे में हम नेक्स्ट वीडियो में डिस्कस करेंगे. सो अभी तक हमने पढ़ा है कोलिजन्स. पावर के बारे में हमने पढ़ा. कॉलिजन क्या होता है? जब भी हम कैरम खेलते हैं, जो भी एक स्ट्राइकर होता है, जब हम स्ट्राइकर से जो कुकी होती है उसको हम जब स्ट्राइक करते हैं तो स्ट्राइकर दूसरी तरफ जाता है, जो वाइट और ब्लैक वाला जो है वो दूसरी तरफ जाता है, तो वो होता है कोलिजन। ठीक है। और इलास्टिक एंड